Math 287, Quest to College. I'm Joe Vasta. We are going to do 1.8. 1.8, I'm going to call it the Euler-Homogeneous differential equations of first order. Okay, your book's going to call it the change of variables, and that's a correct name, but I like to call it what we're solving, Euler-Homogeneous differential equations. Just like the linear differential equations could be called the method of the integrating factor. That's kind of what they're doing the method. So here's a Venn diagram. We have separable equations, linear equations, these are all first order differential equations, and then we're going to study Euler-Homogeneous. Now, lots of books will call them homogeneous differential equations, but it gets a little confusing because we already have another definition for homogeneous when the right hand side is 0, and this is a different kind of homogeneous, and since Euler worked on this, I'm going to call this the Euler-Homogeneous differential equation so we don't get them confused with the other kind that we will see. So there's a Venn diagram, which means there are some differential equations that will be all three. Now we don't even know what this is, so let's get into some definitions. Okay, I'll check the camera here. Perfect. So we have a two-variable function. If you're not familiar with this notation, it's just an expression that has x's and y's. This is homogeneous of degree 0 if and only if f of tx ty equals f of xy for t greater than 0. So what is this? So how is this going to help us solve differential equations? Well, we'll get to that. Right now we're going to ask the question, and you'll see this in your homework, is this function homogeneous of degree 0? So let's go ahead and see this. How would I figure this out? I'd plug in t of x for x and t of y for y. Well, let's see what we get. So this is t times y cosine tx over ty. This is all over tx quantity cubed. Now inside the argument of the cosine, those t's cancel. We end up getting t y cosine of x over y. This is over t cubed, x cubed. And here we're going to have some reducing. We'll end up getting y cosine x over y. And on the bottom we have t squared x cubed. And so that's what we have for this. Does this equal the function f of xy? Well, the thing is, we have this extra t squared there, and that is not exactly this. In order for this thing to be homogeneous of degree 0, you got to get exactly the same function without any t's. The t's are going to go away. So this does not equal f of xy, and the answer to this is f homogeneous of degree 0. We're going to say no. Let's go ahead and do our next problem. And maybe this next problem you can do on your own. So pause the video and see if you can do this. Is f homogeneous of degree 0? Okay, so what I'm going to do is I'm going to go ahead and plug in tx, ty into that two-variable function. So I have tx, where x is, and ty, where y is. So I'm going to square that, and then I have tx cubed. This is all over square root of ty to the 6th power. Okay, so on the top I have, I'm going to just do some algebra, t to the third xy squared minus t to the third x cubed. This is all over. This is really the square root of t to the sixth, square root of y to the sixth. And because t is a positive number, and that was in the definition of homogeneous of degree 0, this thing is just going to equal t cubed, the thing that I have circled. Okay, so on the top I'm going to factor out a t cubed. And on the bottom I have that t cubed from there. And then this is the square root of y to the sixth. You might remember that if t is a real number, any real number, then you would have to have the absolute value of t cubed. Or you might not remember that. Well, in any case, the t cubes cancel, and you end up getting xy squared minus x cubed all over the square root of y to the sixth, which is exactly our function. All the t's went away. This equals f of xy. And the question, is f homogeneous of degree 0? We're going to say, yes, it is. Okay, so our next question is this. This is question 3. It's the same function that we had in problem 2. See right there. Except now they want us to rewrite it in one variable. So that's kind of new. So when the answer is yes, it is homogeneous of degree 0, you can rewrite this 2-variable function as a 1-variable function. So let's go ahead and see if we can do that. So when I do that, I'm going to do a substitution, and this is how we'll solve the differential equations. And we don't even know, we don't see differential equations here, but we'll solve them this way. We are going to do a substitution. Substitution. And our substitution will always be v equals y over x. Okay? So that would mean that y, if you can solve for y there, it equals xv. Now, let's go ahead and plug this everywhere we see a y in this equation. So we're going to plug this everywhere we see a y. Let's see what we get. So we end up getting f of x, comma, xv. I'll just make my v small, I guess. I don't know. It looks like a capital V. Your guess is as good as mine on terms of if it's capital or lowercase. So this is x, and then we have xv squared minus x cubed all over the square root of xv to the sixth. Okay, so what I have then is I have x squared there, v squared, so there's going to be like x cubed, v squared minus x cubed. This is all over. We have x to the sixth under the square root, and then this is v to the sixth. And so to continue, we're going to assume that x is greater than 0. So we won't have the absolute value. So I have an x cubed, then we have v squared minus 1 on the top, and on the bottom I have x cubed, and this is the square root of v to the sixth. And as you can see, those x cubes are out of there, and we have now done a substitution and replaced this 2-variable function with something that just has v's in it. V squared minus 1 all over the square root of whoa, the paper is coming apart there, v to the 6th. And so this is what it is. We could retitle this right here. We can call it like capital F of v, and there is our answer. We have the answer right there. So in your homework, they're going to ask you to do that when they give you a two-variable function that is homogeneous of degree 0. Now, this is a bit optional here, but I'm going to show this to you anyway. We have our definition. Oh, there comes that sun. So this time I have an oar from a canoe that's acting as the block. So you may have remembered, I think it was this class where we were having some sunshine issues where spots were showing on the page. Anyway, here's homogeneous of degree 0, and that was the definition there. Some of you might have wondered, well, what is homogeneous of degree n? Well, that's when f of tx ty equals t to the n f of xy, where t is greater than 0. So we actually can use this more general definition to see that this definition works, because we have here t to the 0, which is just 1. Okay? And then n can be any real number for this more general definition. In this class, we are not, so we're not going to use this. Not used in this class. Okay, so let's go ahead and get to what we really wanted to get to, is what is an Euler-Homogeneous differential equation? Let's show you the definition. So we have a first order differential equation, which we're studying in chapter 1. This happens to be Euler homogeneous if and only if f is homogeneous of degree 0. So the right hand side is homogeneous of degree 0. And if we have that, then this thing is Euler homogeneous. Let's go ahead and solve some differential equations. So when we solve some differential equations, we end up having this right here. So let's go back to this definition. Put it right down here. First of all, when we solve this differential equation, we want to make sure that this thing is Euler homogeneous if this is going to work, and you want to have y prime all by itself. So y prime is going to equal, we're going to divide by xy, and when we do that we have y squared minus x squared all over xy. Okay, the question is this Euler homogeneous? Well, let's check to see if this is homogeneous of degree 0. Now the check is pretty basic. I can do the check over here. I mean, I'm going to put ty in for y. And actually, some of you can do this check in your head. Tx in for x. And so I have tx, ty. You might already see that the t's are going to go away. You can factor out a t squared on the top. So this is y squared minus x squared, and factor out, well, you could just not factor, just put a t squared xy. Oh yeah, okay, so this is homogeneous of degree 0, which makes this an Euler homogeneous differential equation. Now here's the funny thing about this. This differential equation is not separable. See, you cannot separate this function on the right hand side as two expressions where one just has x's in it times the product of the other one, which just has y. You cannot separate this, so this is not separable. And this here is also not linear because we have this y squared here. And we also have y times y prime. So this is a mess, and if you're looking at our Venn diagram, this problem that we have lives right there. So this is a differential equation that we do not know how to solve. We have not solved, and we will learn how to solve that here. Okay, so let's kind of box that off, and we'll use another color here. We are going to rewrite this y prime as dy dx. And I know, some of you don't like that notation, but I'm going to do something even crazier, and I'm going to go ahead and write this as d. So I'm writing dy dx, except I'm putting the y right here. Okay? Make sure it doesn't drop down too far. Make sure gravity doesn't take over, and then that looks like it's on the bottom. Okay, so this equals y squared minus x squared over xy. So what we're going to do is we're going to trick this problem into getting done. Now, how do we do that? With a substitution. We are going to let v equal y over x. That's what we did on problem number 3. If I can find out where it is. See, we let v equal y over x. Okay, and so that will always be our substitution. There are sometimes that this thing would work if you let v equal x over y, but this will always work for the ones we're given. So this means that y equals xv. Now, you might think of this as, when you did integration and you first learned u substitution, you did a u substitution, you were tricking that function into being a function that you can integrate. And that's what we're doing here. We're tricking this equation into an equation that we will be able to solve. So how is that going to happen? Well, I'm going to go ahead, and since we're doing a substitution, everywhere there's a y, I'm going to go ahead and replace it with the xv. So here it goes. D dx, and then we have xv. This equals y squared. So I'm going to go xv quantity squared, or I'm just going to go x squared v squared minus x squared. So that we just leave that one alone, and then this one's going to be x times xv. So this is x squared times v. Okay, now on the left-hand side, we are going to do the product rule, because this is the derivative gun, and we say the derivative of the first times the second plus the first times the derivative of the second. And we're taking the derivative with respect to x, so it's going to be dv dx. Okay, now there's stuff happening on both sides of this equation. How exciting is this? I mean, who needs Netflix when you've got differential equations? I'm going to factor an x squared out of the top. And look what's going to happen on the right-hand side. You are going to cancel those x squareds. Okay. Now, what I want to do is I want to solve for dv dx. To solve for dv dx, I'm going to subtract a v on both sides. So I have x, and then dv dx equals v squared minus 1 over v minus v. Okay, so I want to get a common denominator over there, and the common denominator is v. And we are going to move down to another piece of paper here. And so, what do I have here? I have x dv dx equals, okay, so look what I have. I have v squared minus 1 minus v squared. Let me just write that out. This is all over v. And this is x dv dx equals, the v squareds are out of there, and I have negative 1 over v. So you might recognize what we have here. We have a differential equation. It has x's and v's instead of x's and y's. And this differential equation happens to be separable. So we did a v substitution to trick our original differential equation into being a separable differential equation. So let's go ahead, and now this is like 1.4 skills where we're just going to solve this. Separate the x's and y's. So when I do that, I'm going to multiply both sides by dx and multiply both sides by 1 over x and multiply both sides by perhaps a negative v. In any case, it doesn't matter which side you put the negative on. I'm going to get negative v dv equals 1 over x dx. Okay, so that was separation of variables. Hopefully I think I did that correctly. And you know, I mean, you could have kept the negative on that side. It doesn't really matter. I'm going to go ahead and integrate both sides. The integral of negative v is negative v squared over 2. I'm going to put the plus c on the right hand side. And then this one's going to be ln absolute value of x plus c. Okay, so now I'm going to multiply both sides by negative 2. We'll put that right here. And I'll end up getting v squared equals negative 2 ln absolute value x minus 2c, which happens to be a constant, c. Okay, now I think it's time perhaps to go like this. There was my substitution. It says v equals y over x. So I'm going to go ahead and plug y over x into that v. So this is going to be y squared over x squared. And this equals the right hand side, which does not have any v's in it. Okay, so I went back and I put it back into y's, and now I'm solving for my y's, or y squared. So I'm going to say y squared equals negative 2x squared ln absolute value x plus cx squared. So I multiplied both sides of the equation by x squared. Now some of you would say, well, can't we just write that as c? Well, we don't really want to do that. It's only when we have a number times c. When you have a variable times c, you cannot just replace that with another constant. Otherwise, you could just say that's c, and then c plus this is c, and then c will always be your answer in every differential equation. So you can only do that when you have, like we had here, negative 2 times c gave you c, but you can't, when you have a variable times c, you cannot change that to a c. We can solve for y and write it as plus or minus the square root of that. I'm going to go ahead and leave my answer like this. As long as I have my y's on one side and my x's on the other, I think I'm going to be good with this. Some of you may have factored out, you know, maybe you'll look in the book. Okay, so here's a good point to make. The book might have y squared equals negative 2x squared, and then they'll go like this. ln absolute value x plus c. So you might say, how could that be? This c right here is different than that c. Okay, so this c right here, you know, if you multiply this back through, it looks like it says negative 2x squared c, which that negative 2c just becomes the c. So just be careful when you're doing your problems and you look at the answer in the back before you tear up your homework and run out of the room screaming. Just slow down and say, oh, okay, that could be the same answer. Let's go ahead and do another problem. So this is basically the skills that we need for doing this. And we are at 24 minutes. Okay, perfect. We hear the airplane flying over. That's kind of cool. And we're going to do problem number 2. So here is problem number 2, which looks like this. Wow. Okay, kind of looks like problem number 1, but I think it would be great for us to do another problem, just work this through and get used to the idea of our V substitution. And so this is the reason maybe your book calls 1.8 change of variables, because that is the method. We are changing some variables around. Once again, I like to call these sections what kind of equations we're solving, and this is an Euler-Homogeneous, or is it? Let's check. The first thing we want to do is solve for y prime. And when I do that, I get 4x squared plus 3y squared all over 2xy. Okay, that's a y there. And to check, you can put tx there and ty there, and then here's a tx and ty, and you'll find that the t's can factor out of the top, and you'll have a t squared that cancels with a t squared. This will work. Now, if you didn't check to see if this was Euler homogeneous and you did your substitution and you found out you could not get rid of all the x's, then perhaps you didn't have an Euler homogeneous one. Okay, so let's go ahead and do our substitution. Our substitution will let v equal y over x. Okay, and so then y equals x times v. So there's our substitution. Remember the y prime, what we did last time? We went like this. We said y prime is d dx times y. Okay, so that's what we have. I'll just write out the right-hand side again. This is 2xy. Okay, so everywhere there is a y, I replace it with an xv. I'll change colors. And so what I have here is I have d dx, we have xv equals 4x squared plus 3xv squared, and then this is 2x, and then this is xv. Now, on the left-hand side, we have the product rule, and every time you do a problem and you're doing this substitution, the same thing's going to happen on the left-hand side. So, derivative of the first times the second plus the first times the derivative of the second. So, after a while, you might just start memorizing what happens on the left-hand side. On the right-hand side, I'm going to factor out an x squared from the top. So, I have on the top, it will be 4 plus 3v squared, and on the bottom I'm going to have this x squared with a 2v. The x squareds cancel, and I end up getting this expression right here. With this expression, I'm going to go ahead and subtract the v. Okay, so it's kind of similar to the last problem. dv dx times x, and then we have 4 plus 3v squared over 2v, and then we are subtracting a v. So I need a common denominator. My common denominator should be 2v. So 2v, I need 2, and then here's a v. And maybe we could actually finish this problem on one piece of paper, but who knows what will happen. We have x dv dx equals, so I have 4 plus 3v squared, and then I have minus 2v squared. So that's just going to give me 1v squared, or just a v squared, plus a 4. This is all over 2v. Okay. Now what I'm going to do is I'm going to recognize this as a separable equation. And with the separable equation, I'm going to put the x's on the right side and the v's on the left side. So on the right side, I'm going to have a 1 over x dx. And on the left side, I'm going to have 2v all over v squared plus 4. This is dv. The next thing I'm going to do is I'm going to integrate both sides. When I integrate both sides, I see that I'm going to do a u substitution here, but really I'm going to eyeball this one. The derivative of the bottom is right on the top, so that's going to disappear, and the integral is going to become the ln of the absolute value v squared plus 4. This is going to equal the ln absolute value x, and then we have our plus c here. Well, hopefully you can see that this absolute value is not needed because v squared plus 4 is always positive. And the next step here is I'm going to exponentiate both sides. I'm going to e both sides. Okay, so this thing right here, where's my blue pen? This thing goes pop, and so I end up getting v squared plus 4. On the right hand side I have e to the ln absolute value x, and then I have e to the c. This thing right here is just going to become another constant, so this right here is another constant, and I have v squared plus 4 equals c, this thing goes pop now, times the absolute value of x. Now the absolute value, we are going to have to go to another piece of paper. Where are we? I don't know. Nah, I think we can fit this. The absolute value is going to be absorbed by the c. So we have cx. And I'm going to change the v, so look at, I don't know why I'm pushing that up there. The v is actually going to equal y over x. So this is y squared over x squared plus 4 equals cx. So I'm going to come up here. Wow, so this is getting pretty pathetic. Maybe I should have used another piece of paper. I'm going to solve for y squared. So I subtract 4, y squared over x squared equals cx minus 4, and then I'm going to multiply both sides of that equation by x squared. So y squared equals cx cubed minus 4x squared. I could actually square root both sides, but I'm not going to. I have y's on the left side and x's on the right side. There is the answer to the differential equation. And hopefully you followed all those steps. So I'm at 32 minutes. Let's go ahead and do one last problem here, and that will complete 1.8. So this is problem number 16 in the book. We're going to go ahead and do this problem again. You probably don't need to see another problem. So some of you might be alright with just shutting off the video and cranking out your homework, but you know, maybe we should do this. I have y prime equals this, and what we're going to do is, you could verify that this is Euler-Homogeneous. I'm going to do that. Okay, so T, Y, ln Ty minus Ty ln Tx. This is all going to be over Tx. Okay, so what do we have here? Let's see what we have here. We have, I can factor a t out. So these t's right here, if I factor that t out, it's going to cancel with that t. And then we have y ln ty minus y ln tx all over x. And so it might appear that the t's are not going away. Factor out a y. We have ln ty minus ln tx. This is all over x. And we can use the quotient rule of logarithms that says we can go ln, what is this? Ty over tx. This is all over x. The t's do cancel, and I end up getting the same function Of course, I can undo the quotient rule of LNs and get exactly that. So this guy really is, the right-hand side is homogeneous of degree 0, which makes this an Euler-Homogeneous differential equation. So let's go ahead and solve this. How do I solve this? I'm going to do a V substitution. I'm going to let V equal y over x. The way I remember this is that y prime is dy over dx, so that helps jog my memory on that. I have y equals x times v, so that's going to be my substitution. Everywhere there is a y, I'm going to go ahead and replace that. Now on the right hand side of the equation, as we saw in many of our problems, I mean, this guy right here is dx of y. So I'm not going to write out the whole equation again. And we have this, this, and this, and this. Let's go ahead and do this problem. We end up doing dx of xv. We've seen that 2 times already. And then I have xv ln xv minus xv ln x. This is all over x. So what we have here is so it reminds you of what we did on that other piece of paper when we verified that this was homogeneous of degree 0. It's going to kind of be the same thing where we say, hey, look at these, this x can be factored out, and then we can cancel it with that one. And I didn't change colors. Oh well, I'm just going to continue using the black ink here. And then this is v times, we have the ln of xv over x. Okay, so doing a lot of stuff there. And on the left hand side, I end up getting v plus x dv dx. Okay, so that's what I've been getting in the other problems. And so you can see the x's cancel here. And x dv dx equals v ln v, and then we have minus v, because I subtracted v on both sides. And so this differential equation is separable. We have just tricked this guy into being separable, and I'm going to separate it. I'm going to have a dv over v ln v minus v. This is going to equal 1 over x dx. It seems like that is always going to happen when we do these equations as well, if you look back at problems 1 and 2. Integrate both sides, and maybe I've learned my lesson. I'm going to go ahead and use another piece of paper here. And wow, so the integral of the left-hand side looks rather crazy. I mean, look at this. Let's factor out on this side here. Let's factor out a v, and then I have ln v minus 1. Okay, and we'll just keep the right-hand side exactly the same way. Okay, so now I'm taking a look at this right here. The derivative of that is actually 1 over v minus 0. The derivative of the ln v is 1 over v, so that's going to disappear, and I'm going to have the ln of that orange thing. And so let's go ahead and write that down. ln of the absolute value of ln v minus 1. This is going to equal the ln absolute value x plus c. Okay, I'm going to exponentiate on both sides. On the left-hand side, that's going to go pop. On the right-hand side, that's e to the ln x times e to the c. E to the c is c, and then that other thing is going to go pop. And so when everything is settled, I'm going to get ln v minus 1, the absolute value of that, is c times the absolute value of x. Okay, so that's what I'm going to get. If you're kind of wondering how I went from here to here, you can take a look at the last problem when I did that, and I think that's what I got. I got c times the absolute value of x. Now the c can absorb both of those absolute values, so I have ln v minus 1 equals c times x. Now we're almost done with this. I'm going to add 1 to both sides. ln v equals c times x plus 1. And we're going to go ahead and e both sides again. Look at this, or exponentiate. And that thing there goes pop again, but there's no log over there, so we're going to keep the right-hand side the way it is. I'm going to get v equals e raised to the c times x plus 1. That's in the exponent. And I'm going to replace that that v with, see, v gets replaced with y over x. And so that's what I'm going to do. So this is y over x equals this right here. And so my final answer, I multiply both sides by x, I get y equals x e raised to the cx plus 1 power. And that completes problem number 3. That also concludes 1.8 lecture, and we'll see you guys next time.